Hi, everyone. Today we're going to do some practice Clojure problems to go over the basic concepts that we've done in the last two videos. And for these problems, we're going to use this really cool site called Exercism, which has a bunch of different tracks in many different languages. I think it has tracks in all the languages that we're having in the Paradigm Conference, except for APL maybe. And they have this large repository of problems that you can practice on, as well as mentors on the site who review your code and give you tips and feedback. So it's a really great place to practice. And today we're going to take a look at some of the basic Clojure problems on the site. So without further ado, let's get into it. So the first problem is a very hello world-like problem. It's super simple, but we're just going to do it to review some basic concepts. So the way it's phrased is that we're cooking some lasagna and we need to define some functions and variables to help us with this. So the first thing we want to do is define the expected oven time in minutes. So define the expected time variable to be how many minutes the lasagna should be in the oven, and we're told that's 40. So we're just defining a variable. Super simple. We use def expected time 40. And I don't think we've explicitly gone over this, so I'm just going to show that we can load this main.clj file into our REPL. And that will load in the variable expected time. And we have 40. And I'll also point out that you notice it says sort of hashtag user/expected time. So this is referring to the fact that we're in the user namespace, and namespaces are these distinct areas in which we can define functions and variables, and those definitions are specific to that namespace. But that's a bit more complicated of a Clojure topic, so we won't go too in-depth to it right now. Just know that this is referring to the namespace that we've defined the variable inside of. So our next task is calculate the remaining oven time. So define remaining time, a function that takes the actual minutes the lasagna has been in the oven and returns how many more are left. So we know that it has to be in for 40. So if we've only been in for 30 so far, 10 minutes are left. So again, this is really simple. We can define a function like we saw last time. And so I'll just give it t, standing for the time it's been in so far. And we do minus expected time t. Remember, when we're doing the minus function, we think of it as going after the first argument and before the second. So this is expected time minus t, and expected time is going to be greater than whatever time we give it. So we want it to be in this order. So we can just copy and paste this to reload the file in. And now remaining time is defined, our function. So say it's been in for 35 minutes, 5 minutes are left. Okay, part 3. Define the prep time function that takes the number of layers of lasagna you added as an argument and returns how many minutes you spent preparing the lasagna, assuming that it takes you 2 minutes to prepare each individual layer. Okay, so again, this is a super easy thing to do with what is it layer time, the name of the function? Prep time. This is super easy to do with the skills we have so far. We just take an L for layer times 2L, because each layer takes 2 minutes. So prep time of 2, like they gave in the example, is 4. And now calculate the total time to create the lasagna. So this function will take 2 arguments, the number of layers we added and how long the lasagna has been in the oven. It will return the total time we've spent on the lasagna, including how long it took to prepare the layers and how long it's been in the oven. So if we look at their example, we see 3 layers times 2 equals 6 minutes, plus 20 minutes in the oven, 26. So there's 2 different ways we could write this function. Both are equivalent in a sense. We could do it like we've been writing our other functions. So total time, so this time we're taking an L and a T, and we're adding the time we've been in so far with 2 times the amount of layers, because that gives us the time it took to produce those layers. And in this case, that's not very unreadable. That's completely fine. But since we learned about these last time, let's try and do this using a let block. So now we're going to find the layer time times 2L, 2 times L. And now our final expression that we return is simplified down to t plus layer time. So this is a bit more verbose, and for a problem like this, it isn't really necessary, but it's easier to intuit what the code is actually doing because we were a bit more explicit. So now we can load in both of these and check total time 320, 26, total time 2, 320, also 26. So both work. In this case, this one is probably the better one to use, but this sort of idea of using let blocks within our functions to define intermediate values, and then having a very simple returned expression, which is just a function applied to those intermediate values, that is something that's going to become more idiomatic as we design more complex functions. It's because it's easier to read and easier to reason about. So that was a super easy problem. Let's try one that's a bit more complicated. So we're going to try and do the problem that Pepe had left you guys with at the end of his video, last video. So I'll just quickly review it. We want to define a function called toFor. And if we give it a name as an argument, it returns one for name, one for me, the string. If we don't give an argument, it just returns one for you, one for me. So the bell should sort of be going off in your head that we have this case where we have a variable number of arguments that we want to give to our function. So one way we learned to handle variable arguments last time was with, let's see, with the ampersand symbol. We put it in front of a variable, and that variable can be an arbitrary vector of arguments. However, this doesn't work for the case where we give it no arguments. It's still expecting at least one argument. So it can be one or more, but it can't be less than one. What we have is a case where we might have 0 or we might have 1. So we're going to define a multi-arity function. So let's just review multi-arity functions. They sort of look like this. We have different function bodies depending on how many arguments we get. So if we get no function arguments, that's the empty case. We'll say, let's see, one for you, one for me. In the case that we do have an argument, we want to use the string function to join 1 for with whatever that is, and then comma 1 for me. Okay. And so this is still a pretty simple function, but now we're using the more complex idea of multi-arity. So let's see, toFor. So we call it with nothing, and it says 1 for you, 1 for me. If I call it with my name, it says 1 for Rohan, 1 for me, and that works for any string. So I could type in a string of nonsense, and it would apply that same idea. So again, pretty simple function. Now let's try something a bit more difficult. So we're going to try and reverse a string. So it doesn't need much of a description. You give it a string, you get it out. There are a lot of ways to do this, and perhaps some of the better ways. We haven't gone over the tools to do that yet. So we're going to use everything that we've gone over in the videos and try to solve this problem. So what's the first hard thing about this is we have this all clumped together. For example, the word cool. We need a way of splitting these letters up. We want them each to be an element that we can sort of move around. How do we do that? Well, we can try something like, oops. This might not work. Slightly broke this here. Let me reload. So one annoying thing about the REPLs is sometimes we get in this frozen state. Okay, that key sort of ends it. So start the Clojure REPL again. It might actually try and reinstall Clojure. Okay, no, it still has it in. Okay, so Clojure.string. So here's what we did here. So this did work. I was slightly unsure for a moment, but it seems like this does work. So Clojure.string/split, that's a function. And this is, again, I mentioned the idea of namespaces. This is from the Clojure.string namespace, which has lots of functions specifically for working with strings, as you might intuit. And so we don't have these loaded into the core library whenever we start up our REPL. We have to explicitly load them in. So for example, in Python, this is like importing some other library that comes with the Python language, but is not loaded in as soon as we start writing code. And the same idea in other languages as well. So we give it the word we want to split, and then we use this hashtag. So you might remember these hashtag symbols can be used to define anonymous functions. We can also use them in this case to describe regular expressions. So this is sort of a regular expression saying split and every character. So now we get this list of characters. So let's try and build up our function at the same time. So reverse string. Okay. So we're going to get a word. And we're building it. We just built up this intermediate representation that is useful. So let us use a let block to sort of assign this to a name. So we're going to say letters. So we got this letter representation of our word in a vector. And we did that by saying clojure.string / split with this regular expression. So now we have letters defined. Now we need to try and reverse them. So Clojure is a functional language. So let's try and think about the specific tools we have at our disposal, which might enable us to reverse the string. So we went over 4 sort of main higher order functions last time, and those were the map, filter, reduce, and apply functions. So let's start with apply, because we can sort of eliminate this example pretty easily. Remember, apply takes in a function and a vector of arguments, and then it applies that function to those arguments, but there's no vector anymore. So we already are in this sort of state where we do have a vector, and we could sort of imagine applying where each one becomes its own character, its own variable. So each character is bound to its own variable, but that becomes kind of messy. Like, how are we going to know what variable is assigned to what name? Doesn't really seem like it'll be very helpful. The map function, so we can sort of map some function across each character, but so we could get, for example, a vector that looks like F applied to C, F applied to O, et cetera, et cetera. However, this only transforms this specific value to sort of, it doesn't move things around, right? We're applying a specific function to C, but that doesn't really help us change its position with respect to the other elements. Again, filter doesn't look like it's going to be helpful. That's for removing things from a list. We have everything in this list, this vector, and we want it to stay there. We don't want to remove everything. So we're left with reduce. And so reduce will sort of take some operation. We'll give it some function, and it will reduce that function with C and O, and then it will take whatever we get from that and then do the same thing with O and do the same thing with L. So it's sticking these things back together. And that seems like it would be useful for us because we want to stick them back together. We just want to stick them back together in a different way. So let's pretend our word is it's not a word anymore. It's just a string CO. And we've just turned it into this format of vector of C and vector of O. And we want to reduce a function that will flip the order. So let's see, we could try something like, and I'll do this in the REPL. So we could try reduce. We want a function that switches them back together in the opposite order. So we can just string the second, then the first. So the string function to join the second to the first, and then map that over, or reduce that, sorry, over our vector of letters. Okay, so we get OC. We just reverse that. And let's see if this actually generalizes to our more complex case. Okay, Control D is exit from the REPL. Go back in. And to make this easier, I will define L to just be this handy little vector, so we don't have to type this all out on one line. Maybe make the window a little bigger as well. Okay, so L is this. Now we want to reduce. Function over L. Okay, so we see this actually does generalize, which is really nice because a lot of the times a solution to a simpler part of the problem won't be the same for the whole thing, but we did actually reverse the word cool. And so let's go over what again happened. Well, we take the first 2 arguments, then we join the second to the first. So now when we apply the function a second time, our first argument is CO and our second argument, sorry, our first argument is OC and our second argument is O. So we do the same thing and we join the second to the first. So now we have OOC, and then we continue this onwards until we get LOOC. So this problem that seemed like it was really hard at first can actually be solved very elegantly using a functional approach. If we really wanted to, we could even make this. Trying to think of a good name. We could make this function assigned to a name as well, inline, something like this, and then just call that function down there. But since it's so simple, that would be %1. Since it's so simple in this case, we'll just write it out all in one line. So letters. Okay. So now let us save that and then load our new file in. The reverse string is here. Okay, and let's see if they give any more examples. Let's try a word we know to be a palindrome, like race car. So we should get back out race car. Okay, so it seems like this works. So again, this is a lot more complex of a function than something like this, but it's not necessarily more complex in that it's longer. It's more complex in that we have we're doing all of these, not all of these, but we're doing a few sort of complex functional operations. That doesn't necessarily translate into a function that looks much longer, but it translates into a function that has more of an intention about it. So we are defining this intermediate value, then we're also defining this mini function inline as an anonymous function. We're reducing that function over our intermediate value, and that's our solution. And it sort of speaks to the expressivity of Clojure that this isn't all that much longer than the much more simpler toy function that we wrote earlier. So that problem was a bit challenging. Let's try one more challenging problem. And this problem is called Armstrong numbers. And this will actually require us to import some external libraries, I think. So that will also be a good skill that we'll learn from this. So it says an Armstrong number is a number that is the sum of its own digits, each raised to the power of the number of digits. So that's a bit confusing, but let's look at some examples. 9 is an Armstrong number because 9 raised to 1 is 9. 10 is not an Armstrong number because 1 raised to 2 plus 0 raised to 2 isn't 10. So what we're doing is we're splitting the number up into its digits and then raising those each to a specific power and checking if the number is equal to those summed together. Okay, so now that we have a good understanding of the problem, let's try and break it down into parts again. So again, we have this similar issue of having this one unit, in this case, a number, and we want to split it up into its specific parts. So how we did that before is we use string/split, but we're getting a number, not a string. So we might think that we want to convert that number into a string and then split it up into its individual characters, which are in this case the digits, because each character of our string of a number will be a digit, and then convert those to integers, and then we get the digits. And so that's a bit of a roundabout way. And I'm not sure if there's maybe an easier way to do this, but that's how I'm going to try and solve that right now. So also it's worth mentioning, I'm not sure if you guys have noticed, but predicate functions in Clojure, for example, the empty function, it tests a condition. That's why we call it a predicate function. It tests if a list is empty or not. So empty vector, true, empty with a filled vector, false. They end in question marks so that we know they are testing some condition and will return a true or false. So to keep to that standard, we'll also call our function Armstrong question mark. So it will take in a number. We're gonna have a lot of intermediate values we want to balance. So we're definitely going to want a let block here. So first we want to get out those digits, and we can wrap this nicely into a single expression. We just use this same logic as earlier to extract all of the individual characters in a string. And because our number is not a string, we have to turn it into a string. So we turn our number into a string, get all of the characters. So for example, if we have 108 as our input, that becomes string of 108. And at this point, we now have something that looks like this. But we want everything in here to be an integer. So we haven't explicitly mentioned this, but Clojure is built on top of Java and the JVM, so it can interop with Java. So we can use this function defined in Java, integer /parseInt, give it a string of a number, and it returns that number as an integer. And one way we can check this, well, actually, One way we can check this is we can do arithmetic with what we get back. So now we get 11. So we're going to want to apply that function to every element of our vector. So we want to map integer slash parse int over digits. We'll just call that ints or digits int. So the integer version of our digits. So now we have, for example, 108. And we want to apply the Armstrong condition, which is raise each number to the length of the number, raise each digit to the length of the number. So 1 to 3, 0 to 3, 8 to 3, and then add them up and see if they're equal to the number. So we don't have an inbuilt exponentiation function for Clojure in Clojure. So let's write one ourselves. So it takes x and n, where n is the power we're raising x to. So how would we do exponentiation? Well, exponentiation is just repeated multiplication. So we could imagine if we want to raise 5 to 3, we just create a vector of 5 3s and then reduce multiplication across of it. And what that does is it takes the first two 5s and multiplies them, takes the answer from that, multiplies it with the other 5. So we know we're going to reduce multiplication. Now, how do we get that vector? Well, we have this other function in Clojure we haven't talked about yet called repeat. So for example, if I put repeat 2, 5, it repeats 5s 2 times, or creates this expression, this list, in this case, of 2 5s. And now if I want to reduce multiplication across that, I essentially raise 5 to the power of 2. Oops, those shouldn't be brackets. So what we want to do here is repeat nx, so repeat our base n times, and then reduce multiplication. Okay, so now we have an exponentiation function. Now what we can do is map that function over digits int. Now, I don't think we've explicitly talked about mapping functions that require multiple parameters before. So this function is expecting 2 things, but when we map, we're only giving it 1. So for example, if we have the vector 108, we can't just map x of 1 because it needs something else, the power we're raising it to. Luckily, we know what that power is. That power is just the number's length. So we can use the count function on our digits vector to get the length of the number. And now we can turn this into an anonymous function. Because one of those things is going to be constant, so we'll just say this anonymous function takes in the variable argument in this case, which is the base, but the power that we're raising that base, to is set. So we can just pass that in as is, and then we'll create an inline anonymous function here, like that. And this will be, we'll assign this to the value raised. So now we've gotten pretty far towards our problem. We have converted our number to its digits, and then raise each of those digits to the length of the number, the number of digits in the number. The final thing we need to do is add all of those together. So remember, at this point, we have something like 1 raised to 3 in our vector, 0 raised to 3, 8 raised to 3. We need to add all of these things together. And like we were talking about earlier, when we want to apply a function to a vector and have each of those elements become an argument, we use apply. So apply raised. And now we can simplify the actual return value of our function to this very simple expression. Does the sum equal the number? And let's see if that will work. Oops. The file isn't called Armstrong. Too many. Okay. Try that again. I did not define it as a function. I defined it as a variable by accident. Cannot find parse int. That's strange. Didn't I just test it earlier? Now it's complaining. It's unable to find static field %. Is it not able to be mapped? Oh, okay, let's see. For some reason, it isn't letting us map that. That's interesting. And this, I'm assuming, has to do with because of the fact that We're doing Java interrupt here. So I am not too knowledgeable about this either. So, okay, so I guess maybe this is not represented as a normal function in Clojure, so we can't just call it like that. But if we make this a function that we can call by just wrapping it in an anonymous function like this, so normally this would be sort of unnecessary because whatever we're giving it is a function. In this case, for some reason, it's not interpreting it as a function when I try to map it over the list of the vector of digits, which I'm still not completely sure why, but we can sort of force it to be a function by, where did it go? By making an anonymous function which calls it. Let's see if I'm able to resolve simple sum. Oh, okay. So we always have to make sure our expression is inside the let block. So all the values we defined inside there will still be valid. Okay. Okay, so that is an Armstrong number, which is true. 100 is not an Armstrong number, which is false. And so that is the behavior we'd expect. So yeah, these were a good sort of diversity of problems to experiment with today. We sort of learned how we can use those things that we played around with in the videos, functions, let statements, higher order functions, stuff like that, and sort of compose them into functions that do useful things. So I hope this was valuable to you guys. And if you have any questions about the content of this video, or if I made a mistake somewhere, please be sure to let me know in the comments. Thank you.